Hello.
Good morning, sir. Why is it audible, sir?
It is audible?
Audible,
Yes,
sir.
sir. Yes, sir.
Okay.
Sir,
Thank
thank
you.
you, sir. Thank
Yeah.
you.
Okay. Yeah.
Sir, 1 minute.
Sir, myself, Dr. Nancharaya, HOD of Mechanical Engineering, sir, at
Okay.
Bapatla.
Okay. Fine. Okay. Yeah.
The video is paused due to network connection.
Sir,
I can't.
ఇక్కడే టెక్నికల్ పీస్
Sir, finish. వినిపిస్తూనే ఉంది ఇక్కడ అన్ని వినిపిస్తూనే ఉంది రాజశేఖర్ బాబు గారు మాట్లాడారు చేసాము మీరు వినిపిస్తుంది మీరు మాట్లాడారు కదా అది కూడా వినిపించింది నేను మాట్లాడిన ఇక్కడ నుంచి రికార్డ్ అవుతున్నాను ప్లీజ్ కట్ పెట్టాము వెయిట్ సార్
మనం వెళ్ళి కూర్చుని అరేంజ్మెంట్స్ చేయించుకుని 10కి స్టార్ట్ చేసేద్దాం సార్ 12 కల్లా క్లోజ్ చేసేసారు పార్టిసిపెంట్స్ కూడా చాలా ఎక్కువ మంది
ఏం చేయాలి
అంటే ఏం చేయాలంటే డ్రైవ్ చేయటమే వాళ్ళు వర్క్ టీమ్స్
ఫస్ట్ ఇయర్ ఎప్పుడు వస్తారు
ఆయన్ని తీసుకురమ్మని చెప్పాను సార్ ప్రకాష్
ఫస్ట్ అవర్ అయిపోయింది
సార్
మరి రావట్లేదండి
నాకు పైన మీతో కిందకి
పంపిద్దాం మీరు ఇవ్వండి సార్ ఏం ప్రాబ్లం మీరు వస్తే మెసేజ్ చేయండి మై నంబర్ ఐఎమ్ రెడీ టు గివ్ ప్రస్తుతం వాళ్ళు ఓకే ఇప్పుడు ఏం చేయాలి డ్రైవ్ చేయడమైనా ఏం చేయాలి ఇక్కడ ప్రోగ్రామ్
వాళ్ళ దగ్గర
అదే నేను అడిగితే డ్రైవ్
చార్జర్ కావాలా
ఈ సైడ్
ఛార్జింగ్ వెళ్ళిపోయింది ఛార్జింగ్ వెళ్ళిపోయింది
హలో
అడ్మిట్ చేయండి
అరే బాబు మీరు పార్టిసిపేట్ చేస్తున్నారా క్విజ్లో అరే ఒక ముగ్గురు రండి అరేంజ్ చేద్దాం ఇంకో ముగ్గురు పంపించు
మిమ్మల్ని
కదండ్రా రండి
సార్ స్టార్ట్ చేయండి.
ఓకేనా?
Welcome to second day of second international conference on mechanical engineering and emerging technologies. In day one covered inaugural session followed by keynote addresses and 2 technical sessions. In session 1, 7 authors and session 2, 10 authors have presented their papers. Today, after completion of the keynote address, the remaining 2 sessions follows. Today's session starts with keynote address by Dr. DIXIT, Uday Shankar Dixit. I am handing to convener of the conference meeting.
Good morning. Today dignitaries in the conference hall and as well as on the online. Respected Principal of Bapatla Engineering College, Najir Garu, and colleague professors, participants, and all other persons who involved in this conference, a very good morning to all. So I am very happy that yesterday we started the conference, first day conference. So we successfully completed the inaugural section, keynote address 1, and followed by technical session 2 sessions. Now today, day 2 starts. So in this day, the keynote address is given by Dr. Uday Shankar Dixit Garu, Professor, Department of Mechanical Engineering, IIT Guwahati. So I would like to, on this contest, I would like to thank our keynote speaker, Dixit Garu, so who accepted our request in spite of his busy schedule and having many schedules. Whenever we ask the request, he accept our request and giving a card and giving the moral support. So go ahead. So I will support to you in the form of giving the keynote speech. So thank you, sir. Thank you very much, sir. So without any delay, we are starting this session. So I request Mr. Netaji, please introduce our today's speaker. So please come and introduce our speaker. So once again, thank you, sir. Thank you for your accepting our honorable request.
Dr. Uday Shankar Dixit is currently a professor in the Department of Mechanical Engineering and head of the Center for Indian Knowledge System at Indian Institute of Technology, Guwahati. He received his BE degree in Mechanical Engineering from the erstwhile University of Roorkee, now Indian Institute of Technology, Roorkee, in 1987. An MTech degree in Mechanical Engineering from the Indian Institute of Kanpur in 1993 and a PhD degree in Mechanical Engineering from IIT Kanpur in 1998. He has worked in 2 industries, HMT Pinjore and Indomark Steel Technology, New Delhi, where his main responsibility was designing various machines. Dr. Dixit joined the Department of Mechanical Engineering, Indian Institute of Technology, Guwahati in 1998, where he is a currently professor. He was also the officiating director of the Central Institute of Technology, Kokrajhar, from February 2014 to May 2015. Dr. Dixit has actively engaged in research in various areas of design and manufacturing for the last 3 decades. Most of his research work is focused on modeling of manufacturing processes and involves finite element analysis and soft computing. He has also contributed to design optimization. He has extensively used finite element and soft computing tools for the design and manufacture of mechatronic systems. He has authored 143 journal papers, 145 conference papers, 47 book chapters, and 8 books in mechanical engineering. He has also co-edited 11 books and several conference proceedings. He has guest edited 11 special issues of journals. Presently, he is an associate editor of the Journal of the Institution of Engineers, Series C, and regional editor AC of the International Journal of Mechatronics and Manufacturing Systems. He has guided 16 doctoral and 56 master students. Dr. DIXIT has investigated a number of sponsored projects and developed several courses. He is a fellow of the Indian Welding Society, National Advisory Committee member of International and All India Manufacturing, Technology and Design Conference. He was a board member of the Indian Institute of Technology, Kanpur from 2018 to 2021. He is a reviewer of several journals and has organized several conferences. He has international collaboration with several researchers. His active areas of research include sustainability, analysis of additive manufacturing, and concrete 3D printing. He has executed several social relevant projects such as technology development to upgrade the skills of brass metal artisans of Hajo, Guwahati, and the development of a mission for making plates out of the areca nut. Thank you.
Thank you. So it is a very great opportunity for us with interacting our great Professor Dixit Garu. So I request all the participants place his expert in the your areas so that it is very much useful. Without delaying any time, I hand over to the session, Dr. Dixit Garu. Sir, please continue the session.
Okay, thank you. Thank you very much. Thank you for introducing me. At the outset, I am very much grateful to the organizers of this conference for giving me an opportunity to present my views in this conference. And more than that, I am happy that they agreed to host me online actually. Because of the other commitments, I could not visit. But due to technology, now it is possible that I am interacting with all of you. I am seeing that a lot of participants have joined in this online system also, and many may be sitting in the auditorium. My namaste to all of them. And without much delay, I would start now my presentation. Okay, so let me share my screen. Okay. If there is any problem in audio video system, then please tell me. Okay, before, is it my screen is visible? Can anybody tell me?
Sir. Yes, sir.
Yeah. Okay. So yes, so today I want to give talk on this aspect, that modeling and simulation of manufacturing processes. And this is the place where presently I am sitting. Now I understand that this MEET conference involves the researchers from all domains of mechanical engineering, manufacturing, design, thermal, and other aspects. So therefore, I have chosen a topic which should be of interest to everybody, because I am talking about modeling and simulation, in which people from thermal engineering side, people from design side, and people from manufacturing, everybody contribute and make the manufacturing processes better. And in between, I'll be also discussing some experimental aspects also. So it is, I have about maybe about 40-45 minutes time. In that time, I would try to give one exposure, because it is not possible to cover all the aspects in depth. So this talk will be more wide rather than deep actually. So interested people then they can further explore, or they can be in touch with me through emails, etc., and we can discuss more about that. And they can of course refer to my publications as well as related publication of other researchers. So Now, why modeling and simulation has become very important? We know that this is the era of Industry 4.0. And what do we mean by Industry 4.0? There are various definitions given, but without going into that, I am just highlighting that these are the essential elements of Industry 4.0. One is artificial intelligence, AI, very important, that machines can take decisions like human beings. Then Internet of Services, and Internet of Things. Okay, means even objects are connected by internet, you all know. Cloud computing, lot of data is maybe in the cloud, it may be that available in the website, and we can do computations on the web. We don't need to have hardware in our organization, but you can work. And then of course the big data and analytics, that is also coming up. A lot of data we have got, and that can be analyzed. So Industry 4.0 term was first coined in Germany in 2001 at one Hanover fair, which is basically a trade fair of Germany. It is very big trade fair. And before that, in 2009, President Obama in America also launched that strategy for American innovation. Then concept of Society 5.0 was launched by Japan. Society 5.0 is slightly different from Industry 4.0 because Industry 4.0 highlights the importance of the computer and AI systems, etc., in our day-to-day life, including manufacturing. But Society 5.0 wants to take the human beings and machines in synergy, and it is more concerned about that involvement of the human beings. Human beings should not become redundant. They should learn to coexist with the industry. And they made in China initiative, of course, and our Prime Minister also took initiative about Make in India, which has four main pillars. That means emphasis is on in developing new processes, new infrastructure, new sectors, and new mindset. That means new mindset means it is not that I will be designing something only by experience, but rather maybe using IT tools and all those type of things. So, in these things, particularly new mindset, you understand that there is now importance of the modeling and simulation of the processes, because practically we have been doing the work since ages by hit and trial and learning. But now it is a time we can utilize the computers in a big way. So this is what, so he also now took initiative about Digital India, for which digital manufacturing also is naturally a part. Digital manufacturing, a process that uses computer systems to create, simulate, and optimize manufacturing processes. We can simulate the processes. Then 3D printing is also part of digital manufacturing, because we are basically printing everything by computer. Just like we take a printout, we are now taking the printout of the actual object. Then computer aided design, of course, very important, simulation software. And then by using digital models of products, manufacturers can test designs and simulate production processes to identify and address potential issues before physical production begins. Then digital manufacturing also enables customization and personalization of products, as digital designs can be easily modified to meet specific customer requirements. So we can have now mass customization. We can make for each and everybody, we can make the specific product. I was just thinking that suppose you go to a cloth shop and you want to purchase some t-shirt, okay, so then generally the shop has about maybe 10-15 varieties of t-shirts, maybe 20 varieties of, but population is huge, so the t-shirts will become common. But if you have that your proper digital manufacturing, immediately the t-shirt can be made which will have unique design for everybody, and it will be only slight modification of the design it will become a unique design. So basically the same thing can be done with every product. And then digital manufacturing can also help to reduce waste and environmental impact by allowing for more precise and efficient use of materials. It is often used in combination with other advanced manufacturing technologies like robotics, artificial intelligence, and the Internet of Things. Nowadays, we are also talking about digital twin. This is a new type of topic, although basically research in that direction is going on since decades. But the now in a big way, digital twin research is coming up. It has become a buzzword. Digital twin is a virtual replica of physical model or processes. It is mainly used for controlling, monitoring, and evaluating the performance of the physical model or process under consideration, and real-time monitoring of the manufacturing processes using digital twin enables the manufacturers to improve efficiency and throughput. The ease of the availability of data captured from sensors has made it much easier to create digital twins. Now, if you want to make a real digital twin, naturally you have to do modeling and simulation of the process beforehand. Then only you can make a digital twin. This was mostly first used by NASA, and this is you see that this is actual rocket which is going in the space, and this is that in the virtual space the same thing is happening. So it is like a digital twin. That means whatever is happening that in the space, same thing you are seeing in your computer screen. If anything is going wrong there, you are trying to correct from here itself, and you are controlling, because obviously you cannot go in space, you are controlling from the ground. So it was highly needed for NASA to work on the digital twin. Similarly, after that, people started making digital twins of many things. You just see that this is one oil rig. It is on the offshore, and it is so it is obviously very difficult for all the staff members to be present there, but a digital model of this can also be made, and you can control the plant from distance. So basically, to summarize that, why do we simulate manufacturing processes? So if we be specific, then manufacturing processes are simulated for estimating the forces, loads, which helps in designing machine tools, dies, also useful in predicting life of tools, dies, and job accuracy. We want to know details about that. Then to estimate product quality, dimensional deviation, surface finish, surface integrity, we want to know what will be the microstructure and hardness. Some of these things are somewhat easy now because the techniques have been well established, but some techniques are difficult also even now. So let me first explain that what is the difference between modeling and simulation, because many times we use these words modeling and simulation interchangeably. Even topic of this talk is also modeling and simulation of manufacturing processes. So basically, model is the representation of the processes that provides some information about it. Anything that you make, it may not be the actual process, but it is something of the process. It may be telling the partial information, or it may be making full information. It can be a physical model, or it can be a computational model. So model gives information about the process, and execution of model is called simulation in the computer terms. Suppose I make a model, that means my model means I will be putting a lot of equations, mathematics. I write the computer program, and finally I will be executing you by giving different input values. I will show you results. Those will be called simulation. So two types of models are used. One is the direct model, other is the inverse model. Both are important. Direct model means you give me input parameters, I will tell the output. And in the indirect model, inverse model, it gives that if you give me the output that this is what we are getting, then what will be the input? That type of thing is also done. Suppose I say I got this type of surface finish. Then okay, if you got this type of surface finish, your feed must be in this range. like that this type of answer comes. So naturally inverse modeling is difficult because it depends on so many parameters. If you give the less number of parameters, then inverse modeling will not give unique answer. But nevertheless, it is very important because many times we do not know the properties of the system and we do not know even its behavior, then inverse model can help. So now simulation, as I said, that simulation is an approximate imitation of the process. Simulation is the imitative representation of the functioning of one system or process by means of the functioning of another. So it can be that simulation can be done basically in hardware way also. That, you know, like for example, Weber makes a simulator where you can study the material behavior which comes in metal forming, etc., on the actual machine, and by doing some experiments there. But mostly nowadays it is used in terms of the computer. Okay, so simulation, modeling, and analysis is the process of creating and experimenting with a computerized mathematical model of a physical system. Then we say simulation and modeling. So now let us be specific that what are the manufacturing processes. When we talk about, particularly in the context of mechanical engineering, there are these important processes. One is the machining, which is a subtractive manufacturing process where we subtract the material, we remove the material to make a shape. Then metal forming can be called mass containing, where we just change the shape of the metal. If I have got a rod, I can just bend it and it becomes a mass containing process. Casting is also mass containing. Metal forming and casting, in one sense, they are similar, that you take the same amount of material without wasting much and you make the shape. Only thing is that in casting there occurs phase change from liquid to solid, and in metal forming solid remains solid only, but it is also flowing like liquid, but it is a solid. In casting you just make in liquid form and then it goes there. Then powder metallurgy. Powder metallurgy, you know that if we have material in the form of powders, then it can also produce that this one. It is also similar to casting. Only thing that here you have powder and it has to be compacted and sintered. Then you get this process. Then joining, that means welding and adhesive bonding, where you join two materials. And 3D printing, now which is called the additive process today, which is something like opposite to machining. Instead of subtraction, you are doing addition. You keep adding the material layer by layer and you get 3D printed projects. So let me just show you that we generally go to shop floor and we see typically these machines. This is doing turning, lathe machine, then this is drilling, this is milling, and nowadays we are having many non-traditional machining processes. I just picked up one to put here, that is electrochemical machining, which is a very good process. It can use precise dimensions and all those type of things, very good surface finish, but has a drawback also, that not very sustainable. Its electrolyte is not good for environment. So I heard that in some countries it is banned also, but in our country, of course, we are using. So we have to be careful about the wide use of that, and particularly we need to develop something sustainable electrolyte rather than electrolyte which will harm the environment. And then typically this is machining. Now coming to the metal forming processes, these are the processes that cause changes in the shape of solid metal parts via plastic deformation. And we have bulk metal forming and sheet metal forming, two type of things. So in that example is that you have rolling process, and here you have extrusion also. It is a bulk metal forming. You are pushing it and doing, and you can have forging. This is open die forging, and this is closed die forging. You know that connecting rod of automobile is made by a closed die forging process. And then wire drawing, you can make very thin side of wires. And in sheet metal forming, you have many things. Even the punching and shearing is also considered sheet metal forming. This is a deep drawing process where it is making the deep cup type of things. So many processes are there, and nowadays in the metal forming, you can do metal forming by laser also. Not only the machining. In machining, laser was employed since many decades, but nowadays people are even deforming the material by heating, by thermal effect only. So we see that here in our lab we have deformed the material. This is very thick one also, but it has been deformed in a better way than mechanical deformation. We have made this circular arch type of things, cup type of things, and even very difficult, like even very material which are not so ductile, they can also be deformed because they have been heated. And this is laser, that was only laser bending, but this is laser assisted bending. That means I am putting mechanical load also, but I am making use of the laser to soften the material. We make it soft, and that's why that here and then it bends very easily. So that means heating is done to change the material property, and load is applied in a mechanical way. And then there are say something, there is a Japanese term origami. Origami means making the toys using papers. We make many things by paper. So similar way, the sheet can also be deformed by laser heating, and that type of thing is also done. There are now industries which are using laser origami. Now these were the metal forming process to make a new product, but metal forming processes can also be used for improving the properties of the material. So among them we have the severe plastic deformation processes like equal channel angular extrusion, that where you extrude it and it makes the 90-degree bend, again you go back, like that again and again you do. Shape is not changing, but microstructure will improve and you will get high strength. Similarly, you see that this is a small disc, and your material is that one die is rotating and also applying the pressure. So combined pressure and torsion, it also puts a lot of strain hardening, and you get a better quality of the material. Similarly, you can have a cumulative roll binding, where we just roll the material, then its length becomes bigger, then you cut it into pieces, again stack it together and repeat that process. So purpose was here to get good properties of the material. Now the challenge is only that they have to be applied to industry scale. In lab they have done very good job, but you know that we don't want that you demonstrate this phenomena on a small size of material. It has to be done at a bigger scale. So that challenge is there for you young engineers. Okay. Now similarly you can do even hydraulic autofrettage, like suppose you take a cylinder and pressurize it, so it plastically deforms in the inside and outside. Green zone, it is elastic only, and if you remove the load, then the plastic zone will not come back, but elastic zone tries to come back. So in a way it puts a pressure on the plastic zone, so you get generated residual stresses. Those compressive residual stresses, they help us a lot because they nullify the effect of the stresses due to loading. So even here at IIT Guwahati, we developed. So in IIT Guwahati, we developed thermal autofrettage process, and this is the same type of thing which is done by hydraulic pressure in the previous slide, that is done by means of the thermal means. Okay, so we just create a differential temperature and it creates ultimately the residual stresses here. Okay. So similarly, we have rotational autofrettage process. Rotational autofrettage means that suppose it is rotating at a high speed, then you get those centrifugal stresses, and if you and they make even cause plastic deformation. Once you remove the load, then there is a compressive residual stresses. In fact, this process has been conceptually developed, but so far not even a single experimental paper has been published on this process. In 2016, it was first paper of UDAY. So in fact, there is a lot of scope to do the experiment on this rotational autofrettage also. So anyway, by giving this brief exposure about various processes, let me now tell that what is the objectives of the modeling and simulation of manufacturing processes. So these are the objectives. One is the power requirement. We want to know how much power in this process will take, pressure in the die and tools, stresses, strains and strain rate distributions in the material during processing, then residual stresses in the product. Residual stresses are very important. They remain in the material. They are like a silent stresses. You will have compressive also and tensile also simultaneously. But in the surface, if you have compressive stresses, they are better, but tensile stresses are bad. So not many people pay attention to residual stresses because modeling is also difficult, but experimental determination is also difficult. You need some techniques also, but this is worth paying attention because residual stresses do come in machining as well as other processes and even 3D printing also. And they are the major, this one have impact on the life of the product. Then defects, many type of defects, the geometrical accuracy, surface integrity, mechanical and metallurgical properties, and microstructures, they can be predicted by proper modeling and simulation. So before that, okay, I'll just show that in additive manufacturing, we have got various processes, solid-based, powder-based, liquid-based, but that I think you are familiar with that. Every process has got some special features, and this is just, I am just passing this one. So you see that we have even FDM, inkjet 3D printer, okay, selective laser sintering, where you just sinter the powder material. All these type of processes have become very important, but in this area, that modeling is still needed. Modeling efforts are there, but they are limited actually. So let me just briefly tell that nowadays when we do modeling, we use the new techniques. Either it will be finite element based, or it will maybe soft computing based. But I just want to give a brief summary of the modeling efforts, and some of these techniques are still useful. They should not be thrown away, although their importance has diminished, but they will be very helpful in before you make the actual model in a computer. These type of analytical methods, etc., are also important. So one such method is SLAB method, which is in fact taught in the undergraduate classes also, that where you just make a slab of that and then you make a differential equation of the process. This is, by this you can find out the forces in rolling, wire drawing, any type of things. So in 2000, we have published a paper that about that when by slab method we are producing the curvature in a sheet, actually asymmetric rolling. Okay, so suppose the speeds are different, then how do you, it takes curvature, and then you have to write many equations based on the taking some slab, force variance in x direction, y direction, and momentum. Then these have to be solved by numerical methods. Okay, computer will still be needed because you cannot solve that. Then there is a strip line method which just tell that it is also based on the equations, but it is for only plane strain type of problem. So limited importance. Here we assume that the material flows along the strip lines, okay, along some 45-degree lines to principal stress like that. And based on that concept, we have got mathematical equations. Then you can find out indentation of a semi-infinite medium by a punch. You can find out by strip line method how much load will be there, that you can find out. Even in machining, you can use strip line method. You see in 1951, etc. also they were used, but that doesn't mean that now they are not. Even recently, such type of papers are published, not that much as in FEM, but you see that 2017 paper, theoretical prediction of machining induced residual stresses in 3-dimensional oblique milling processes. In this work, stresses in the hand zone are evaluated using strip line field theory. So you can still see this. It is a very good journal. You can see that in this one. Then upper bound method, it was introduced by Hill in 1950, and it can give you an estimate that it is upper bound. That means power can be this much, maximum power can be this much. and lower band method is just the counterpart which tells about the lower band, lower bound. And visioplasticity method, of course, this is almost nil nowadays, but it was a semi-analytical method. First you make a grid pattern in your material, then deform it in process, and then you analyze that how much deformed grid looks, and based on that you do analysis. But nowadays, you know that basically FEM has come starting from 1970s. So here you have to solve the equation. If you want to tell that what is FEM in very in a half sentence, then you say that FEM is a method of solving differential equations. Finite element method is a method of solving differential equations. That means you should have a differential equation, then only you can apply FEM. Otherwise, you cannot do. So that one has to understand. So what differential equation we use? We use continuity equation, we use equilibrium equations of the material. That means basically Newton's law. The understanding this thing has become more important because nowadays you have ready-made packages which will solve your problem, but you do not know that ultimately which differential equation is getting solved. Many students are not able to answer that question. So therefore you have to pay attention that actually I am solving this differential equation. Lucky I don't want to, I do not have to write the code because code has been already written in the package. So, and there are some techniques. One is Lagrangian formulation, where it is a control mass approach, and then Eulerian formulation. That means in one we follow the particle, so particle path is followed, and in one we stand at one place and see how many things are going. Like I am standing here, I am seeing one car has passed, one truck has passed, and after that something else will. So these are the things. So our Lagrangian processes will have difficulty because more computational time, and in fact residual stresses are not predicted properly, and some boundary condition application may be also tough. In Eulerian, of course, as I said, that you stand at one place, say in the bridge, and see how many things are passing. So you make a control volume and make that type of things. But there will be equations in in this also, and these equations will be like this, and Levi-Mrs. plastic flow rule. You have to understand the equations, and then strain hardening behavior, continuity equations. So there are many techniques of doing that. Luckily now the packages are there, like penalty method, mixed pressure velocity formulation. And how do we solve the simultaneous equation? It is not that you can solve only Gauss elimination. You have to use, say, other methods. Like one such method is Householder method, which can solve these type of things. So in the coming days, of course, because the packages have become very efficient, you will not get much opportunity to develop the codes for that, because commercially they have been added. But it is a request to all the young engineers that they should try time to time, they should read these papers in which detailed description is there, so that they can know that what is going on inside the package. So this is my, that in long, during my PhD long back, that I made a FEM model, and this is shown the boundary condition, wrote the package, and after that, then there were some difficulties, like some spurious pressure term was coming. So later on, my student, after 10 years or 12 years, my student published a paper, and he modified my own analysis. By doing that, he combined, in fact, finite element and finite difference together, and also he used neural network and with for computations, not for experimental data, but computations only. And with that, he got the better result. So we show that DIXIT and DIXIT model is this. My predictions were in dotted, but present model means my student's model. You see that it is very good result is coming. Similarly, other case also means my prediction was also okay, but students model also give good result together. But our prediction for roll force was little bit higher because of the not proper calculation of the hydrostatic pressure, but this was done. So this paper was published in 2008 in ASME Journal of Manufacturing Science and Engineering. Okay. And similarly, for other material also, we see that you see my model was giving huge error, but then after modification, my student's model, it gave very good result. And this is what this one. Similarly, that for other material also, is, both the models, and you see that our model and this is experimental, and here both the models are giving this one. And this was the result. My model was shown here, but you know that present model is this, and slide method, which is approximate model, it came close to now by present, means new model. That and this is what. So now just there are some points that when you do any numerical things, small things matter a lot in numerical accuracy. Say for example, there is a formula Ts is equal to F time Tn. F is the friction coefficient, N is the normal stress. Now, question is that in FEM, should you directly find out Ts by equation or by using this formula? So sometimes if you use this formula, you may get better result. This is that, my results of the wire drawing, this I did long back, and you are seeing that results are coming matching with the experimental results. And numerical aspects are in fact very important, because sometimes if you do numerical mistake, then results can be very funny and very this one. Say for example, this is one result from one paper. You just see that if the friction is increasing, then the roll torque is decreasing, and this cannot be happen. This is clearly due to numerical error. If you do proper simulation, then you can find out even the characteristic of the material very nicely, and some defects also. Say for example, in a particular situation, you see the plastic zone has become very narrow, so chances of bursting or cracking is there. That type of thing also you can know. Similarly, similar type of behavior we know in the rolling. Uh, in all these processes, friction modeling is also very important. We have been usually told that friction Coulomb's model, but Coulomb's model doesn't work well. It works at a low normal stress, but after that it becomes more or less saturated. That means friction force doesn't increase with the load. And this is a Vineham and Bay model, which shows that how the transition takes place from Coulomb model to this model. So these things are very important, and friction varies with temperature and amount of plastic deformation also. In fact, still that if somebody wants to do the research in friction in manufacturing, lot of scope is there, but I must warn that the area is very challenging, very difficult to get some breakthrough. Lot of conflicting reports you are getting in the literature. So coefficient of friction, we did this one, and then you see, because friction is dependent on so many things, so very difficult to predict the friction. There may be chemical aspect, lubrication, sulfur oxide film, tooling aspects, what type of tool, material aspects, thermal aspects, mechanical aspect, many things are there. In fact, in machining, we stress normal stress varies like this, and the friction stress varies like this. In the beginning, there is a sticking type of friction, and then there is a sliding. And then another phenomena is in isotropy, which can also be modeled by FEM. So in isotropy, then thermal modeling. Now you see heat transfer and thermodynamics can also be applied in manufacturing. In fact, nowadays, if you want to model 3D printing or anything, you have to do thermal modeling also. So manufacturing engineer's job is very difficult if he is doing modeling, because it is not you cannot say that this is not my subject. So heat transfer. So you see, I am modeling the rolling process, and in what way we are modeling that type of thing is shown that. So both the models, deformation and thermal model, and then lot of materials model. This is also usually we easily apply sigma is equal to K epsilon in Halluman's law, but this is not the only thing. The thing may be dependent on strain rate, and temperature. This is Johnson-Cook's model, and there are many other such models nowadays which are used. Then you can assess the flatness of the sheet, etc. It is not only the forces, but and you can find out like curvature modeling of foil rolling. This becomes even more difficult because lot of elastic deformation takes place. So how the foil will be modeled, and this we try to do inverse modeling at our IIT Guwahati. In fact, this rolling mill was developed by one MTech student. I think it is written something 2000 IITG 2001 nameplate is there if you see here. So it was MTech project, and in that he made the complete rolling mill. In fact, he wrote to one company to purchase the 2 rolls. He said that this much small quantity we cannot supply, but since you are doing for your MTech project, we are sending free of cost, only just you pay the postal charges. And then finally that it came and we fabricated. So we keep doing small experiments here, and we are seeing putting a camera to assess the velocity, then IR camera for measuring the temperature. So by measuring its slip and temperature, then we are going to predict that what will be the property. So it is inverse way. So we are doing that, and by inverse model we are getting the data, and then we put the actual data, both are matching together. And then we also attempted something. There is one good book by Leo that is called Moving Beyond FEM, that is messless method, where you don't make any mess, and but there are only nodes, and we gave in one problem in axisymmetric forging, and we did, but I could not get, frankly speaking, couldn't get much better results than FEM, and there are a lot of challenges. So I am telling that if you just want to do some work and publish paper, maybe this is a potential area, but very difficult, because till now it is still at the only research stage, but people are doing something. So these were my results. Actually, this was published in 2007. And then nowadays, to increase the computational efficiency, you can use a hybrid methods. That means you can combine neural network and FEM model. That means with FEM, you train a neural network, and then trained neural network will be helping your FEM. So this type of similarly AI-based methodology, that we can make the model. We keep doing so many things, computations, but a lot of time my data gets waste. So if I can store that data, it can be used for training some artificial intelligence module. So this phenomena, I am depicting it from this chart. You just see that in the beginning, that if I wanted to do a precise object, I had to, even in simulation, I had to do 8 iterations. Okay, 8 times I do, then I get the what will be my proper parameter. But then by the time, that means 7 data are wrong, but those will be helpful in training the network. Next time it will require only 6 iteration, then the third time it will require less iteration, and finally it will require only 1 iteration. So this is the concept. Based on that, we have done many things. You see, first time, if I made the first job, it took me 7. Like, the first one, suppose a worker has been given some jobs. So first time he's making job to your satisfaction, he may have to make 7 times, then only you will be satisfied. But by that time, the worker has become intelligent, and therefore he takes less time. That is the computation in the simulation. Then we are in fact also doing phase transformation modeling, that how the phases change. Okay, this is not much work has been done, because it involves the person should take interest in the metallurgy also and mechanical engineering also, both. Okay, mostly nowadays metallurgists do that, experimental type of work, and in mechanical engineering, CFD, FEM, and all those type of things. So people have to join hands, and then it can be done. All you have to develop interest. This is a time temperature transformation diagram. You see austenite, pearlite, bainite, all those type of things, which was not taken into account in mechanical engineering modeling. Now you can do with the help of computational tools, and we can use many commercial packages like this. I did in ANSYS, some bending of the sheet, and by that many things in simulation you can see the details also, that what is happening, which may not be possible to see in the online system. So we are seeing that how the temperature is changing, how the bending is taking place. First it is coming in this direction, then changing the direction after 1 or 2 seconds. And microstructure and properties, etc., can be modeled. You have to use, say, some equations like this is for kinetics of diffusion-based transformation, like changing to martensite. Suppose austenite suddenly becomes martensite. This is a diffusion. No, this is not a diffusion-based. This is called just transformation. Diffusion means slowly the carbon is diffusing. So in the quenching, you get mostly the non-diffusion transformation. But in diffusion-based transformation, you are having something like that. With time it is happening. So time term is there in exponential way. You are achieving this one. So this equation is there, and these parameters can be determined experimentally. So you can make a simulation code in which you have thermal module, you have mechanical module, you have metallurgical module, and heat from up deformation goes there in the thermal module. Again, thermal thing influences mechanical module, and we modeled, say for example, laser bending process. Okay, I am heating the laser sheet and it gets bent. So I am predicting hardness of this one sheet by modeling the phase transformation, etc. Because I know that what is the hardness of a phase, so I can predict the hardness of the whole strip, and these are the results. They have been matched with experiments. And similarly, phase fractions, how they change with time or distance. So these type of things are also there, Bainite, ferrite, and what you get. So now let me just, in this slide, I just give one summary that in machining, suppose, say for example, machining everybody does, but it is still very difficult to model. In 1940s, merchants analysis was done. 1950s, slip line field solutions, 3D analytical models. 1970s, finite element became popular. 1990s, mechanistic models and soft computing came. 2004, one Atkins model was there that you find out energy of creating new surfaces. And in 2000s era, that now you are having molecular dynamic simulation and CPFEM, crystal plasticity finite element method. And even the processes like finite friction still welding can be modeled. So I am not spending much time now. I'm just showing you that we have modeled this also, that friction still welding, and this is spot welding. And then we have modeled the 3D printing also something. This is not my result, but there is one model in 2018 that is for predicting about tissue printing, and in connection with that model that can predict the dimensional accuracy, and this one. So these are the some results. And then there are say molecular dynamics. One technique is there. Molecular dynamics means each and every particle you model. So that means, but they follow the Newton's law, and they have some potential, etc. So these are the equations. And then another technique is crystal plasticity, where you go to crystal level and you consider that it is an isotropic. There are some slip directions in which the deformation will take place. So that concept you understand, and then you develop crystal plasticity one, and you write different type of equations here. So we just compare that some case studies. This work I presented in a conference. It is in association with one group in the basically Laplo University, Dr. Anish Rai and myself. So we said molecular dynamic simulation. We took the different type of papers and we analyzed that how both work. So here that suppose single crystal machining is done by diamond crystal. So these are molecular dynamics results, and these are that this one and these are this is single crystal, this is polycrystal, and then you get this result. And the same thing we do by crystal plasticity, and we also get here results. Okay, so I am just showing you going through the results. This we are making group, but I am just highlighting you conclusion. There are two approaches, molecular dynamics and crystal plasticity. Molecular dynamics is useful when underlying deformation mechanism not well understood. If you could do the molecular dynamics, then each and everything you can predict, because you are going at atomic level, be it 3D printing, be it heat treatment, be it machining, be it metal forming. You don't need to understand anything. You just see that how molecule is behaving. So that way it is basically the panacea for all. But the thing is that it gives fundamental insight of the deformation process and no prior knowledge of the system evolution required. But then why we are not shifting to that? Although there are now free codes also available in the net, one can do that, but very difficult because increased complexity of the potential and computational cost. That means if you want to simulate, maybe you will take days and even years. Whatever I am doing by FEM in 10 hours, it may take 10 months here. Time scale and domain sizes are very limited, and unrealistic strain rate you have to give, otherwise at a slow strain rate it will take again more time. Whereas the crystal plasticity FEM computationally more efficient, capability to model reasonable spatial and time domains, various deformation models can be modeled, material with different crystal structure can be modeled, deformation mode dependency on various parameters can be incorporated, and capability to investigate individual deformation mode. But basically phenomenological material large needed, means you need lot of experimental data, etc. Then only you can do, and involves identification of deformation modes and all these type of things. So it is very means compared to molecular dynamics, it is very fast, but you should have enough data from the physics of the process. So basically these two processes in brief I ended my talk by telling that molecular dynamics and crystal plasticity FEM, which will become popular in the coming days. Crystal plasticity FEM means it is FEM only, but using the concept of crystal plasticity. And I also give that exposure about other processes also. So I hope that it was some useful in terms of giving exposure to you. And I thank you for your kind attention. If there are any questions, I would be happy to answer. Okay. Yeah. So
Audience participants, please, any questions?
Sir, mic, sir.
Audience participants, any questions? Participants, any questions?
Good morning, sir.
yes.
Thank you for your excellent presentation, sir. You have covered the topic of finite element analysis and its application in manufacturing, the key different types of manufacturing process and its simulation. Thank you very much for your excellent presentation, sir. Will you throw light on the modeling of additive manufacturing process, sir? Whether if it is FDM, field deposition modeling, we need to do differently. If it is 3D printing, selective laser sintering, we need to do differently. We cannot combine all these things in the same platform. Will you please throw light on modeling of additive manufacturing systems, sir?
Very good, very good. Yes, yes. So recently we tried to study various processes. Like one is the fused deposition modeling, which is basically plastic extrusion. That means you heat the material, it comes out. And other is that you can have even welding type of things. We have directed energy deposition, where you have arc welding type thing and it deposits. So modeling of both the things will be different, and how one should go ahead. Luckily, we have a lot of data in the similar processes. So from there, you get some equations and ideas, and you combine there in your model. Say, for example, I wanted to do about FDM, that how much force, etc., is needed, and what should be the nozzle size. So we took the data from plastic injection, because injection molding data is there. So in injection also the material behaves. So we need not invent everything right from the beginning. You don't need to reinvent the wheel. You take the data from those papers you have to study where they have told the plastic extrusion. Then you will get a lot of data about the material flow characteristic and match this with your own work. That this one. Similarly, if you want to do that about arc welding, like nowadays cold metal transfer is very becoming popular for making the 3D printed part at a fast rate. There we basically melt the wire and it keeps on depositing layer by layer. So we do not have much data on the modeling of these processes, but luckily we have a lot of papers on the welding modeling. So the 3D printing person has to study the papers related to welding and suitably adapt it for that purpose. Okay, so this way it has to do that. Okay. Okay, so I hope I have answered your question.
Thank you, sir. Thank you very much, sir.
Okay, yeah. Yeah, there is one more hand. I think Shiv Shankar wants to ask something. Yeah, he has raised the hand.
Any more questions from the audience? I think there is a question
in this one. Actually, there is a question in the good morning, sir. It is done by software and it does not cost more. In case if you want to do a practical project work, how much cost will be? It would be. Yes, naturally, Ajay Kumar is asking this question. If you want to do it practically, then naturally it is this one. So nowadays, the trend is all over world is that we do not eliminate the experiment, but we reduce the number of experiments. So by simulations you can do, and then you have to do the experiments also. So I suppose that later on, because now there are so many colleges, my proposal is that some central zones can be made. In fact, Government of India is also trying that. They are trying to make some technology innovation hubs in various places where all the people can come together on a specific topic and the work can be done. So that is the answer to this question. Yeah. If there is any other thing that somebody raised the hand, some Shiv Shankar was there, I think. Is he still there? How much difference between practical and software work? Yes. Yeah. That difference keeps on reducing actually. See, I am telling that if there is a new process, your simulation may be quite different from the experiment. But as I said that with time, you will gain experience, you will fine tune your result, and then the difference will diminish actually. Yeah. So nowadays our prediction, it is just like weather forecast. You see, 50 years before in my childhood, you know, if the meteorological department will say that it will rain today, it will not rain. And if they say that today it will be sunny day, it used to rain. But nowadays weather predictions and weather forecasting is very accurate. So same thing is there with the modeling and simulation. If we do more and simultaneously do experiments, then day by day our accuracy will keep on increasing. But unfortunately nowadays many people only do modeling, they never do experiments. And similarly, some people do only experiments. So need is that both the things have to be done together. Then my accuracy of the model will improve. Okay. So that is this one. So yeah. So there is one Shiv Shankar wanted to ask whether he's able to connect or not. He's raised the hand, but in online system. Yeah, Shiv Shankar is there. T Shiv Shankar. If he can unmute, then he can speak. Yeah. You want to? Yeah.
Yes,
you
sir.
can,
In the conference also, by mistake it was raised.
By mistake, he said. Okay, okay, fine. Very good. Okay, good. So then, yeah.
That's all, sir. There are no more questions. Thank you,
Okay,
sir.
thank you.
For giving a wonderful lecture on modeling and simulation of the manufacturing process on behalf of the organizing committee of IC Meet 2023. So I would like to thank you, sir. So thank you. Nice meeting you, sir. Just right. I
Yes.
met you during 2019 at IWCWM, International Conference on Computational Methods in Manufacturing. You at IIT Guwahati presented a paper intern that was published in Springer. Thank you, sir. Thank you.
Yes. Okay, okay. Okay.
Also, I met you in Anna University also for another conference.
Okay, okay. Yes, yes. Thank you. So nice to meet you after long time, and after this one, at least on the right way. So hope we'll meet sometime in physical mode also. Very good.
Sure, sir. Certainly. Thank you, sir. Thank you.
Thank you. Okay.
Right, sir. Thank you, sir. Thank you.
Thank you very much, sir.
Respected participant, the technical session will be starting after 5 minutes.
15
That
minutes.
15 minutes break, and after third session is over, immediately fourth session will come in. So we'll be completing the conference by 1 or
Next immediate session.
okay. Thank you.
Hmm.